Hi, this is a video for 14.3, the assignment where we're doing calculations for the M1 criterion, which is to do with changes of temperature in materials, calculating how much energy is required to change the temperature, and for calculating how much energy is required to change the state or change the phase of the material. So we have, for materials, there are three phases of matter. You have solid, liquid, and gas. Now, if you take a block of solid, some solid, and you put heat energy into the material, then it will change temperature. And the same thing for liquid. You can change the temperature of it, and gas. As long as it stays solid the whole time, you can change the temperature. As long as it changes, it doesn't change from solid to liquid, liquid to solid, liquid to gas, and so on, then the temperature will change. But if it changes phase, then there is no change in temperature. So this is during the time that your block of solid is solid, the temperature will change, and it requires energy to do that. And it requires energy to change the temperature of a volume of liquid. It requires energy to change the temperature of gas. When you have phase changes, they take place at constant temperature. So there is no temperature change. So for example, when ice changes into water, that's a phase change. It's going from solid to liquid, and that happens at 0 degrees C. And we're going to see we're going to need that for the calculations. And when water changes to steam, that takes place at 100 degrees C. So this is the melting point, and this is the boiling point. Also, if water changes to ice, that takes place at constant temperature of 0 degrees C, and when steam condenses into water, it also takes place at a constant temperature of 100 degrees C. So this is going either way, melting point, boiling point. If you took some water and it's not at the boiling point, so it might be at 80 degrees C, so if I take water, it's at 80 degrees C, it's not at the boiling point, I put energy in, that will raise the temperature because it's staying in the liquid phase. Then when it reaches the boiling point, the temperature will stay at 100 degrees C until all of the water has changed into steam. And then when it's all steam, it's then all gas, and we can have a temperature change as we continue to put energy in. But during this thing, although the temperature stays the same, it still requires the input of energy. And if you plot a graph of, so this would be energy, the heat energy. The heat energy you put in is denoted by Q. That's not the unit, that's just that is the symbol for heat energy. Now, start raising the temperature of my solid, and then it turns into liquid, and then it becomes liquid here. So it's all liquid here, and the temperature is going up, and then it changes to gas. Okay, so there we go. That's what it would look like graphically. We're putting energy in, it's going along the x-axis, and the temperature is also going up here, but then when it starts to change from solid to liquid, that happens at a constant temperature, and so does the change from liquid to gas. So that's what happens there. Each material requires a different amount of energy here to raise it by the same amount of temperature. So we have specific heat capacities those specific heat capacities are different for each type of material that you might be considering, and also each phase of matter has a different specific heat capacity as well. So ice, water and steam, they all have different specific heat capacity as well. That's actually why the gradients are changing there as well. So when you have these phases here and you're looking at how much energy is required to change the temperature, you use delta Q equals mc delta theta. Delta theta, that's the temperature change, so just do the larger temperature minus the smaller temperature. There. Okay. Then if you have a phase change, there you use the latent heat here, and it requires a different amount of energy to change one type of material from solid to liquid and liquid to gas, and the liquid to gas and the solid to liquid values are also different. So that's why we have latent heat. You have latent heat of fusion and latent heat of vaporization. So delta Q is equal to m times LF, and delta Q, delta theta, MLV. You've always got the mass values in these equations. Mass must be in kilograms. So you've got to be in SI units for these calculations to work. Right, so you've got those. If you have a case where you start off with some solid at some temperature, which is not the melting point, you put energy in so that it reaches the melting point, and then it melts and it changes into liquid and then raises the temperature, you need to use a combination of these calculations. So you'd work out firstly the change in temperature required to heat the solid from the temperature it started at to the melting point. Then you would need to work out how much, so this is solid to liquid, how much energy is required to change it from solid to liquid, and then work out how much energy is required to change the temperature from its melting point to whatever temperature it finished at. So that's using a combination of these equations. What I'll do next is show a couple of examples where I'll go through this calculation, this calculation and this calculation, and then I'll do some preliminary calculations where you do all of them at the same time. Okay, so the first calculation, which I'm taking from the handout that we've given for 14.3, this calculation is to calculate the amount of energy required to heat up some water from 18 degrees C to 50 degrees C. Okay? Now, there's no change of state here. Water, the melting point is 0 degrees C, the boiling point is 100 degrees C, and at no point are we crossing either of those two things, and the question makes clear that it's staying water throughout. So the equation we need to use is delta Q equals mc delta theta. Now here I'm just going to write in that because it's water, we're using the specific heat capacity of water, so that's C subscript W. The question gives us the data we need to know. Firstly, we've got the temperature change. Whenever you do the temperature change calculation, always deduct the smallest value from the largest value. Okay? So now let's put our values in. The question tells us that we have 150 kilograms of water. It's 150. Because it's in kilograms, there's no need to do any conversion into SI units there. It's already in SI units. C is, for water, is 4,200. And the temperature change, as I said, do 50, the largest one, minus the smallest temperature. That's 50 minus 18. So that's 32. Okay, so 150 times 4,200 times 32, that gives us 20 times 10 to the 6 joules, which is 20 megajoules. If if we wrote it using a prefix. So that's the first example for you, just using the specific heat capacity equation. Second one is to calculate using the latent heat of fusion. Here what we're doing is we're freezing 120 grams of water. There were additional details, they're on the handout, but not here. So this time we need to freeze this amount of water, and we're given the latent heat of fusion. Always look at what information is given to you. Now, here we need to use delta Q equals M multiplied by the latent heat of fusion. So you see we're using a different equation here because this is freezing, so there's no temperature change here. Freezing always takes place at a constant temperature. For water, that's the melting point of 0 degrees C. So there's no temperature needing to be put into this equation here because of the constant temperature. So delta Q is equal to, it's 120 grams, right? So we need to convert 120 grams into kilograms because this calculation should be done using SI units. So M is 120 divided by 1,000, which is 0.12 kilograms. So now we can put that in, that's 0.12 multiplied by the latent heat of fusion, which is given to us as 3.34 times 10 to the 5. Right, once we've done that, multiply those out, that's 4 times 10 to the 4 joules, and that is equal to 40,000, so that's 40 kilojoules. There we go. You notice it's a much smaller number than we had previously. Here we had 150 kilograms of water, we had a lot of water. Here we're dealing with 120 grams. Alright, that's the second equation we need to know, and if I just highlight those equations so you can see which ones we've done so far. The third example is very similar to this one. We're just changing the latent heat of fusion for latent heat of vaporization. So here we are boiling 120 grams of water. We've already calculated what 120 grams is in kilograms. So the mass is 0.12 kgs. We now use this equation because it's boiling. Delta Q is mLV. And now we put the values in. The latent heat of vaporization is different to latent heat of fusion. It's 2.26 times 10 to the 6. So once we work that out, we get 270,000. That's 270 kilojoules. Okay, those are the three equations that you need to be able to use, but I've just used them all independently of each other. I haven't actually done a calculation yet, which requires the use of 2 or all 3 of the equations. So the next thing to do is to tackle one of the questions where you have a temperature change leading into a phase change, leading into another temperature change, and then I'll do also one where with both phase changes in and 3 temperature changes. So I'll rub this off and then we'll have a look at that question.